Trigonometric integrals. Some trigonometric integrals we already know how to find. So from basic antiderivatives, we can integrate sine and cosine. We can integrate secant squared and cosecant squared. From u substitution, we know the integrals of tangent x and cotangent x, even secant x and cosecant x. And from integration by parts, we can integrate secant cubed x or even use a power reduction formula on higher powers of secant. But what about other trig integrals? You might have guessed it, trig identities. If the integrand involves trig functions, then we can use the Pythagorean identities or the power reducing identities, and those are going to be the ones we focus on in this section. Let's start by focusing on a particular form of a trig integral. Let's say I want to integrate the product of sine x times cosine x, but sine x is raised to the m power, and cosine x is raised to the n power dx. There's two different possible cases. If m or n is odd, so if one of the powers is odd, we're going to save one of the odd factors and the differential dx, and then we're going to use the Pythagorean identity sine squared x plus cosine squared x equals 1. The other possible case is if m and n are both even, in which case we're going to use either one or both of the power reducing identities to reduce the powers. For our first example, let's integrate sine squared of 3x dx. This does fall under the second case, where both sine and cosine are raised to even powers. Sine is raised to the second power, 2 is even, and cosine is raised to the 0 power, because I don't see any cosine, and 0 is an even number. So we're going to use the power reducing identity that we see over here. We just want to be careful because we don't have sine squared x, we have sine squared 3x. So we need to make sure and replace the x in the power reducing formula with a 3x. So that's going to give us the integral of 1 minus cosine of 2 times 3x all over 2 dx. Now from here, inside the cosine, 2 times 3x is 6x. And then what I'm going to do is I'm going to realize this division by 2 is the same as multiplying by 1/2. So I'm going to pull out that constant multiple of 1/2. So I'm going to have 1/2 the integral of 1 minus cosine of 6x dx. And now I can integrate each term separately. So I have the 1/2 in front times the integral of 1 is just x. And the integral of negative cosine of 6x, we want to make sure and recognize that we're going to need a 1/6 in the front. So we're going to have minus 1/6 sine of 6x and then plus c. So we can go ahead and distribute the 1/2 back in. So we'd have 1/2 x minus 1/12 sine of 6x plus c. And just a quick reminder before we move on, in this step right here, we also could have thought about splitting this up to be 1/2 minus 1/2 cosine of 6x, and we still would have got the same answer. Let's integrate 3 times cosine to the 5th x dx. This falls under the first case because we have cosine x raised to an odd power 5. So we need to save one copy of cosine x and the dx. We'll rewrite this as the integral of 3 times cosine to the 4th x times that one copy of cosine x dx. So the idea here is that if I save one copy from an odd power, I'm always going to be left with an even power. And then I can rewrite that even power as the following. So we're going to rewrite this as the integral of 3 times the quantity cosine squared x squared times cosine x dx. If I have an even power of cosine, then I can rewrite that as cosine squared x to a power, in this case squared. And then once I have cosine squared x, I can use the Pythagorean identity. So we have the integral of 3 times the quantity 1 minus sine squared x all squared times cosine x dx. And from here, once I've made that Pythagorean identity substitution, I'm going to do a u substitution. I'm going to let u be just sine x, and then the derivative is right there. That's what we saved on the outside, cosine x dx. So let's let u be sine x, then du is cosine x dx. I'm going to factor out the constant multiple 3. I have the integral of 1 minus u squared squared du. Now I just have a binomial squared, and I can go ahead and distribute that out to integrate each term. So I have 3, the integral of 1 minus 2u squared plus u to the 4th du. Don't do something crazy there, like distribute the exponent. We do need to multiply it all out. And then the antiderivative is going to be u minus 2/3 u cubed plus 1/5 u to the 5th plus c. And we'll substitute our sine x back into u and distribute the 3 at the same time to get a final answer of 3 sine x minus 2 sine cubed x plus 3/5 sine to the 5th x plus c. Now let's integrate cosine cubed x times sine to the 4th x dx. This falls under case 1 because I have a cosine function raised to an odd power. So if either cosine x or sine x is raised to an odd power, or they both can be, then we fall under case 1, where we save a copy of the odd power so that it turns into an even power. So what I'm going to go ahead and do is I'm going to write this as cosine squared x times sine to the 4th x, and I'm going to save that one copy of the odd power cosine x with a dx in the back. So now I can rewrite cosine squared x using the Pythagorean identity, quantity 1 minus sine squared x. And then I still have sine to the 4th x times cosine x dx. We're set up to start our u substitution. We're going to let u be sine x because we have the derivative saved, cosine x dx. So we'll let u be sine x, du be cosine x dx, and then we're going to integrate quantity 1 minus u squared, and now there's a sine to the 4th x. That's going to become u to the 4th and then du. All right, before I can integrate, I have to distribute the u to the 4th in so that I have terms being added or subtracted. So I'm going to have the integral of u to the 4th minus u to the 6th du. And that gives us 1/5 u to the 5th minus 1/7 u to the 7th plus c. And now we substitute sine x back in, so we get 1/5 sine to the 5th x minus 1/7 sine to the 7th x plus c. Now, just as a quick reminder, like I said, either of these could have been an odd power, or both of these could have been an odd power. If they're both an odd power, then we get to choose which one we save a copy of to stay with the differential. But choosing the higher power would give us more work. So if one power is lower than the other and they're both odd, we should choose to save one from the lower one. Now let's integrate sine to the 4th x all over 5. So we have sine x raised to an even power, and cosine x is raised to the even power 0. So we're going to use that second case where we're going to use the power reducing identities. Let's start by pulling out the 1/5. So we're going to rewrite this as 1/5 the integral of sine squared x squared dx. So now I can use that power reducing identity, 1 minus cosine 2x over 2 inside the parentheses. So I have 1/5 the integral of 1 minus cosine of 2x all over 2 squared dx. Now here, the 2 in the denominator is being squared, so that's really a 4 down there, or a 1/4 that I'm going to pull out. So I have 1 over 20, the integral of 1 minus cosine of 2x all squared dx. And so now I can focus on this binomial that I'm going to have to distribute out. So what I have is 1 over 20, the integral of 1 minus 2 cosine of 2x plus cosine squared of 2x dx. All right, so we use the power reducing formula. We started with sine to the fourth, and now we've applied it once, and we're at a place where we have left still a trig function squared. We have cosine squared 2x, so we need to reduce again. So that's why this power reducing identity is up. Cosine squared x is equal to 1 plus cosine 2x over 2. We have a 2x inside the cosine function, so we just have to be careful and replace the x with a 2x. So we have 1 over 20, the integral of the quantity 1 minus cosine of 2x plus, so now I'm going to rewrite this as 1 plus cosine of 2 times 2x all over 2 dx. We needed a bit more space. All right, so now 1 plus cosine of 4x all over 2. What we want to do is think about splitting this up. So unfortunately, I cannot pull out a 1/2 like how earlier I pulled out a 1/4, because each of these terms would have to have a 1/2 in it to pull it all the way out of the integral. So instead, what I'm going to do is write 1 over 20, the integral of 1 minus 2 cosine of 2x plus 1/2 plus 1/2 cosine of 4x dx. So I'm thinking again about splitting it up. And now 1/2 plus 1 is 3/2. So those are like terms now. And so we can just go ahead and integrate right now. So we can say this is 1 over 20. And then we're going to think about adding 1 plus 1/2. That's 3/2. And the antiderivative of 3/2 is 3/2 x. And now negative 2 cosine of 2x, the antiderivative is going to have a 1/2 come out, and there's already a 2 there. So it's really just going to be minus sine of 2x. And then we've already taken care of the 1/2 with the 1. So now we're going to find the antiderivative here. And a 1/4 is going to come out because this is a 4x. So we're going to have plus 1/8 sine of 4x plus c. And now we can distribute in the 1 over 20. So we have 3 over 40x minus 1 over 20 sine of 2x plus 1 over 160 sine of 4x plus c. Or we could have left the 1 over 20 outside. Now let's look at another integral form that we might see, the integral of tangent x times secant x, where tangent x is raised to the power of m and secant x is raised to the power of n dx. All right, so the first case is if n, the power of secant, is even and m is non-zero. What we're going to do is save a copy of secant squared x. All right, then we'll use secant squared x equals tangent squared x plus 1, the Pythagorean identity, and let u equal tangent x. So the derivative of tangent x is secant squared x. It will be a similar process to the previous integral form. In case 2, what if m is odd? So m is the power of tangent x, and n is not equal to 0. So the power of secant x is not equal to 0. We're going to save a secant x tangent x dx. And then we're going to use the Pythagorean identity tangent squared equals secant squared x minus 1, and we'll let u equal secant x, because the derivative of secant x is secant x tangent x. In case 3, what if n is even and m is odd? If that's the case, you could use either case 1 or case 2. And finally, what if the opposite is true, m is even and n is odd? We have to try other methods, like possibly integration by parts. And note, the process is also similar for when we have the integral of powers of cotangent times powers of cosecant. And so these cases are going to make more sense as we practice and really understanding the relationship of the derivatives. The derivative of tangent is secant squared, and the derivative of secant is secant tangent x, and just really being able to work with the integrand and see what we can do to rewrite these. Let's jump into an example. I have the integral of secant to the 5th x times tangent cubed x dx. And students often struggle more when the secant tangent functions are involved than sine or cosine, and trying to understand which case it is. And instead of memorizing them, it's really about understanding the concept. So let's go ahead and just try something and see what happens. I'm actually going to try the wrong method first, just so that you can see what happens when you get stuck. So let's say I save a copy of secant squared, and I rewrite this as the integral of secant cubed x times tangent cubed x times secant squared x dx. Well, the idea is that if this was the right method, secant squared x dx would be du, so that means u would have to be tangent x. Well, I have tangent cubed x here, and I would have to be able to rewrite secant cubed x to be a function of tangent x, but I can't rewrite secant cubed x using the Pythagorean identity. It would need to be secant squared. So this didn't work to save a copy of secant squared x dx. So let's actually do the right one. Let's go ahead and save a copy of secant x tangent x. So we're going to have secant to the 4th x tangent squared x, and then we'll have that copy of secant x tangent x dx left over in the back. So now we know that this is going to be our derivative. This is going to be du. So our u would have to be secant. The derivative of secant is secant tangent. So I need to leave secant to the 4th, and I need to rewrite tangent squared x as a function of secant x. So I need to rewrite this as secant to the 4th x, and then tangent squared x is secant squared x minus 1. And then I still have the secant x tangent x dx. All right, we are set up to do our u substitution. U is secant x, and du is secant x tangent x dx. All right, so we have an integrand that becomes u to the 4th times the quantity u squared minus 1 du. We'll distribute in the u to the 4th, so we're integrating u to the 6th minus u to the 4th du, or 1/7 u to the 7th minus 1/5 u to the 5th plus c. And then substitute secant back in, so 1/7 secant to the 7th x minus 1/5 secant to the 5th x plus c. Now let's integrate tangent squared x times secant to the 4th x. Now on this one, we are going to save a copy of secant squared x. So we're going to rewrite this as tangent squared x times secant squared x times secant squared x dx. So now from here, again, we want secant squared x dx, the thing we saved, to be du. So our u is going to be tangent. So we want all of the rest of the integrand to be written in terms of tangent. So we're going to rewrite the secant squared x in the middle. So we have the integral of tangent squared x, and then secant squared x, we're going to rewrite as tangent squared x plus 1, and then times secant squared x dx. So now we can let u be tangent x, then du be secant squared x dx, and my integral becomes the integral of u squared times the quantity u squared plus 1 du, or the integral of u to the fourth plus u squared du. They become such nice polynomial integrands. And now the antiderivative is 1/5 u to the fifth plus 1/3 u cubed plus c. And then we plug tangent back in. So 1/5 tangent to the fifth x plus 1/3 tangent cubed x plus c. So this is technically case 1, and the previous problem was technically a case 2 example. Now let's integrate tangent cubed of 2x dx. So I have a tangent function raised to an odd power, but we can't use case 2 from above because we would need at least one copy of secant. So the power of secant cannot be 0 to apply case 2. So what are we going to do? Well, when we have trig functions, we still think trig identities. And the most popular identity we're going to refer to are the Pythagorean identities, but we can't apply that unless I have a trig function squared. So let's go ahead and still save one copy of tangent 2x so that we have tangent squared 2x times tangent of 2x dx. So we just kind of rewrite the integrand so that we can try something. So now that we have tangent squared of 2x, I can use a Pythagorean identity and rewrite that as secant squared of 2x minus 1. And all of that is multiplied by tangent of 2x dx. Okay, so now let's take a look. I have these two terms multiplied by tangent 2x. If I let u be tangent 2x, the derivative is secant squared 2x times 2, but I have this minus 1 that's really throwing me off here. So what we're going to do is actually distribute the tangent 2x in. So we're going to have tangent 2x times secant squared of 2x minus tangent of 2x. So we can deal with each one separately. And this first one is going to work out nicely to be a u substitution, and I mentioned it a bit earlier. If I let u be tangent 2x, the derivative, secant squared 2x, almost times 2 because of the chain rule, we had, right? So we can go ahead and say u is tangent of 2x, du is 2 secant squared of 2x dx. So a half du is secant squared 2x dx. And so this first integral here is going to be 1/2 the integral of u du. And then we're going to have minus the integral of tangent of 2x dx. All right, so now I have 1/2 u squared over 2. And then I have minus, all right, so the integral of tangent 2x. Really, this is going to be another u substitution. If I show the work, I can rewrite this as cosine 2x, I can write this as the integral of sine 2x over cosine 2x and let u be cosine 2x. But this is also something we can memorize. And so I'm just going to jump straight to writing what the answer is. So it's going to be negative 1/2 natural log the absolute value of cosine 2x and then we'll put a plus c at the end of this entire thing. And now we'll plug u back in. So we have 1/4 tangent squared 2x plus 1/2 natural log cosine of 2x plus c. So again, this didn't technically fall into one of the cases above, but it really is just a matter of manipulating it using identities when trig functions are involved. The cases are just kind of a guide. Now let's work on the integral from pi over 6 to pi over 2 of cotangent cubed x times cosecant to the fourth x dx. This is a definite integral, so we'll have to keep that in mind. And the integrand has a product of cotangent and cosecant raised to different powers. It's going to be similar to the tangent times secant integral form. So let's kind of think about what we can make work here. Here, we're going to think about saving cosecant squared x dx. So if we do that, we're going to have the integral from pi over 6 to pi over 2 of cotangent cubed x times cosecant squared x times cosecant squared x dx. So cosecant squared x dx is going to be at least a part of my du. So I'm thinking that my u has to be cotangent. So that means I need to rewrite the rest of the integrand all in terms of cotangent. So the first part is fine, but I need to rewrite cosecant squared x using the Pythagorean identity. So we're going to have the integral from pi over 6 to pi over 2 of cotangent cubed x times the quantity 1 plus cotangent squared x times cosecant squared x dx. This works out great to start our u substitution. U is cotangent x, du is negative cosecant squared x dx. So we're only off by a negative. Negative du is cosecant squared x dx. So let's focus on rewriting this now. The integrand part first. So we'll have negative the integral. Let's ignore the limits of integration for a second. We're going to have u cubed times the quantity 1 plus u squared du. All right, so now these limits of integration, if we leave them pi over 6 and pi over 2, then they're x values. I'm going to go ahead and turn everything into u values. So I'm going to go ahead and substitute in pi over 6 into cotangent. So cotangent of pi over 6. All right, that's 1 over tangent of pi over 6. So 1 over rad 3. Well, that's just radical 3. So that means that the lower limit of integration is radical 3. And if I plug in pi over 2, u of pi over 2, cotangent of pi over 2 is cosine of pi over 2 over sine of pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So we just get 0. So we have radical 3 to 0. Well, we want to be able to switch these so that the lower limit of integration is on the bottom, and that's going to be nice because then it will make this negative a positive. So we have, in our next step, the integral from 0 to rad 3 of u cubed plus u to the 5th du. Now, our antiderivative is u to the 4th over 4 plus u to the 6th over 6. We will not put a plus c because this is a definite integral from 0 to rad 3. So now if we substitute the square root of 3 in, I have the square root of 3 to the 4th over 4 plus the square root of 3 to the 6th over 6, and then minus 0, which is nice. The square root of 3 to the 4th is 3 times 3, so that's 9/4, plus the square root of 3 to the 6th is 3 times 3 times 3, so that's 27 over 6. We would have to have these with common denominators, and then we'd add their numerators, so we're going to get a final answer of 27 over 4. Let's look at an interesting type of trig integral. Let's try to find the integral of the square root of 1 plus cosine x over 8 dx. The way we're going to approach this is we're going to try to use a power reducing identity, but in reverse. So notice the part underneath the square root, 1 plus cosine x over 8, sort of looks like what I have right here uh, as the power reducing identity for cosine squared. The denominator over here is 2. The denominator we have is 8. So we can rewrite 8 as 4 times 2. So the first step is we can write this integral of the square root of 1/4 times 1 plus cosine x over 2 dx. So now the square root of 1/4 is 1/2. So I have the integral of 1/2 the square root of 1 plus cosine x over 2 dx. So now what I have underneath the square root is really close to the right side of the power reducing identity for cosine. So let's go ahead and write it over here and see how we can use it. So 1 plus cosine x over 2 is what we have. So we want to figure out how to go in reverse here. If I look at cosine squared x, it becomes 1 plus cosine of 2x. So the x doubles. Or another way to think about it is that x is half of this 2x here. So in other words, if I have 1 plus cosine x over 2, the inside of cosine squared is going to be half of x, which is x over 2. So 1 plus cosine x over 2 is cosine squared of x over 2. So now I can replace the part underneath the square root with something squared. So I have, I'll pull the 1/2 out, the integral of the square root of cosine squared of x over 2 dx. Now, the square root of cosine squared of x over 2 is technically going to become the absolute value of cosine of x over 2. So we'll just assume cosine of x over 2 is positive to make this work out nicely. So we'll have 1/2 the integral of cosine of x over 2 dx, but with the restriction that cosine of x over 2 has to be positive or equal to 0. And now this just has a general antiderivative. So we have this 1/2 in front, and the integral of cosine x over 2 will be 2 sine of x over 2 plus c. And the 2 and the 1/2 cancel, so I end up with just sine of x over 2 plus c. So it works out really nice. Now, this isn't the only way to find this integral. There's another option. So I'm going to come up here and I'm going to put or. Here's what we could have done. So let's see. The 8 in the denominator, if I take the square root of 8, that's 2 rad 2. So let's just pull out 1 over 2 rad 2. And then the only part that's underneath the square root is 1 plus cosine x. So the strategy here is going to be that we multiply by the conjugate. So we have 1 over 2 rad 2, the integral of the square root of 1 plus cosine x over 1 times 1 minus cosine x over 1 minus cosine x dx. And we know that in the numerator, multiplying by the conjugate, we're just going to get 1 minus cosine squared x. So we have 1 over 2 rad 2, the integral of the square root of 1 minus cosine squared x over 1 minus cosine x dx. 1 minus cosine squared x is sine squared x. So 1 over 2 rad 2, the integral of the square root of sine squared x, and then the square root of 1 minus cosine x dx. Okay, well, the square root of sine squared x is sine x, provided sine is positive. So we have 1 over 2 rad 2, the integral of sine x over radical 1 minus cosine x dx, as long as sine x is greater than or equal to 0. And this integral can be found using u substitution. So I can go ahead and let u be 1 minus cosine x. Du is sine x dx. So our integral is 1 over 2 rad 2, the integral of du over radical u. Well, that's u to the negative 1/2. So the antiderivative is 2 u to the 1/2. So 2 radical u. So the 2's cancel. Let's put plus c. So the 2's cancel. I'm going to get 1 over rad 2. And then radical u. And u was 1 minus cosine x. So I have the square root of 1 minus cosine x plus c. So we got two really different looking answers. They are actually equivalent answers. And the key to that, if you want to go ahead and check outside of this, is the half angle identities from trigonometry. So when trig functions are involved, sometimes we have more than one strategy that we can use, but they all are going to be equivalent answers. They might not look the same, but using identities, we can show that they are equal. Let's try another one that's similar. So let's integrate from 0 to 4 the square root of 1 minus cosine of 4x dx. We're going to use the power reducing identity in reverse, this time for sine squared x. So we can see we have 1 minus cosine of 4x. So let's go ahead and try to start with the fact that sine squared x is 1 minus cosine of 2x all over 2. So what I can do is multiply the 2 to the other side. So I know 2 sine squared x is equal to 1 minus cosine of 2x. All right, I have 1 minus cosine of 4x. So here I have 2 times 2x. So that must mean that this left-hand side would need a 2x. So I have 2 sine squared of 2x must equal 1 minus cosine of 4x. So think about how if I replace this x with a 2x, well then this x gets replaced with a 2x, and that's how it becomes 4x. So 1 minus cosine 4x is 2 sine squared 2x. So we're going to go ahead and replace the part underneath the radical with 2 sine squared 2x. So we have the integral from 0 to pi over 4, the square root of 2 sine squared 2x dx. So now the square root of 2 is radical 2, so let's pull that out, radical 2, and then 0 to pi over 4. The square root of sine squared 2x is sine of 2x dx. Now, technically, when sine of 2x is greater than 0, since we're on an interval from 0 to pi over 4, we know that the outputs between 0 and pi over 4 of sine of 2x are all greater than 0. So we can simply stick with just positive sine of 2x for the integrand. And so I have the square root of 2. The antiderivative is negative 1/2 cosine of 2x. We're evaluating from 0 to pi over 4. So we have negative rad 2 over 2 cosine of 2 times pi over 4, that's pi over 2, minus negative rad 2 over 2 cosine of 0. So negative rad 2 over 2 cosine of pi over 2 is 0, and then plus rad 2 over 2 times 1. Cosine of 0 is 1. So our final answer here is square root of 2 over 2.